Hello, we are here in Chapter 8, Section 1. This is Systems of Equations. And so let's just get started here. This section has actually like 7 objectives total. I took off the final 3, the 5th, 6th, and 7th objective, because we're only going to concentrate on solving systems of equations with 2 variables, not 3 variables. Objectives 5, 6, and 7 dealt with 3 variables. And in this course, our scope only focuses on the 2 variable systems of equations. So the first objective, we're going to solve systems of equations by substitution. Then we're going to do it by the elimination method. And then we're going to identify inconsistent systems of equations. And then we are going to express the solution of a system of equations, a dependent containing 2 variables. So basically, the last 2 objectives are basically when the system has no solution, and when the next system is when the system has an infinite number of solutions, namely the equation itself. Okay, so let's look at the diagrams of what that's referring to. Okay, so we could have a consistent and independent equations when 2 equations. Now remember, equations can be expressed as graphs, and so when you have these 2 equations and they intersect at one point, that system is consistent and it's independent, okay? And that intersection point is the solution, because what that is, that intersection point is a common solution for both equations. So when you're solving the systems of equations, you're finding the solution or the ordered pair that satisfies both equations. The second picture is inconsistent because these are 2 equations that are parallel to each other. They never intersect. Okay, so the red line and the blue line are just running along with each other, but they never cross. And if they never cross, they never have a common intersection point. So we said that is inconsistent. So therefore, those are the ones that have no solution. Okay, the third possibility is when the 2 lines actually not only intersect, they lay right on top of each other. And that was the 4th objective that when we were referring to, is when the 2 lines intersect on top of each other. And that means they're consistent because it has a solution. Because consistent means they have a solution. Inconsistent means they don't have a solution. But this time, the equations are dependent. The difference between independent and dependent is this. Independent basically means they're 2 separate lines and they don't have any commonality. The dependent was, well, where one goes, the other one goes. So one depends on the other. So it's kind of like a follow the leader. Let's let these 2 lines, and that's why that line is actually purple, because if you combine the red line and the blue line, red and blue combines to be purple. So that's why they made that purple. So these are connected lines. Their systems has infinitely many solutions. So the 4th objective is we're going to see that, and we're going to figure out how to write that. The second one, inconsistent, is pretty, everybody knows, well, if it's inconsistent, we write no solution. It's going to be interesting to see how we write, because you can't say every ordered pair, because obviously every ordered pair doesn't satisfy that equation. It's only the ordered pairs that are on that purple line. For example, you can't just say all ordered pairs, because 0, 0 is one of those ordered pairs, and that purple line does not go through the ordered pair 0, 0. So, so it's going to be interesting when we get to that 4th objective to kind of see how we write that solution. Okay, so let's look at an example. We're going to graph a systems of linear equations. Now, we're going to graph the 2x plus y equals -1, and we're going to graph -4x plus 6y equals 42. So what we're going to do is, first, what we're going to do is we're going to solve each equation for y, and we're going to put them in basically slope-intercept form. So this is equivalent by writing the equation in slope-intercept form. So the equation 1 can be written in y equals -2x minus 1, and then the second equation can be written in y equals 2/3 x plus 7 if you solve for y. So which has a slope of 2/3 and a y-intercept of 7. So let's look at the figure 2 that shows these graphs. So if you look at the first one, the blue one, let's say, we have 2x plus y equals negative 1, okay, because the y-intercept is negative 1, has a slope of negative 2, okay? The next equation has a slope of 2/3 with a y-intercept of 7, and that's the red line. So if you look at the blue line and the red line, okay, they appear to intersect in the second quadrant. Now, to find the solution, this method is kind of sketchy because if you try to locate that point of intersection, it's going to be, well, it looks like around negative 3 on the x-coordinate, and maybe look around the y-coordinate of 5, but I could be off just ever so slightly. So you really don't want to use this approach to solve a systems of equations because, first of all, you're only going to get it if the ordered pair is on an integer. If they cross in between the integers, then it's going to be very tough because you don't know if it's going to be 3.5 or 3.6. You're only guessing if that was what the x-coordinate was. So, but even if they're in integers, if you're off just ever so slightly on your graph, it's going to make a big difference at that point of intersection. So you don't want to just use the graph as a basis of finding the solution. You can get a good idea. You can say, well, it looks like x equals negative 3 and the y coordinate of 5, and then go back into both equations and see if it satisfies it. And it probably, I think it does here. But because if you do 2 times negative 3 plus 5, I believe that's negative 1. And then negative 4 times negative 3 plus 6 times 5, I believe is also 42. So I think we got lucky if we get negative 3, negative 5. But the only reason we're so lucky is this is a computerized drawing of that graph. And so it looks like it because it's very accurate. If you're doing it by hand, human error, if you're off just ever so slightly, like I said, it's very tough to get that point. And but the one good thing about graphing, though, is that even though it's not very accurate sometimes, especially even that, you're usually not so bad off that you at least know that you're going to get a solution. Because if two lines are going to intersect, they're going to intersect. If they're going to, so you're going to find that point, and you can say, okay, at some point in the second quadrant. Even if I'm off a little bit, you know it's going to be something in the second quadrant. So when we use the elimination method and the substitution method coming up, then you know the order pad that you actually get is actually a good point. So it's kind of, I use it more of a check than anything else on the graphing, just to kind of see what's going on. But the next techniques that we use, when we first use substitution, the substitution technique and the elimination technique, now these are two techniques of solving a systems of equation. And so, you got to take that for what it's worth. So it's, one is substitution, one is elimination. There are other methods of solving a systems of equations. That's the only two that we're using in this course. Okay, and substitution is best in some cases. Elimination method is best in other cases. Okay, the problem is knowing which one to use. Well, if they tell you to flat out use one of those techniques, you got to use that technique. Okay. So, but sometimes if y is already solved for you, or one of the variables is already solved for you, it's best to use substitution. But on this equation right here, I would have probably used elimination method on this one. So, but I think I'm going to start with this problem right here and doing it by the substitution technique. And so let's look at that, okay? So let's look at solving a systems of equation by substitution. So how do we solve systems of linear equations by substitution? So if you notice, it is the same equation, 2x plus y equals negative 1, negative 4x plus 6y equals 42. So how do we do this by substitution? Well, as the name implies, what we do is we solve for one of the variables in one of the equations. I have two variables in two equations. I could solve for the x and the 2x. I could solve for the y in the first equation. I could solve for the x with the negative 4x, or I could solve for the y with the 6y. So I could solve for either of those four variables, two of those being the same though. But let's see what we're going to do here. Okay, so step one, what we're going to do is we're going to solve for y in the first equation. And you're like, why do they do that one? Well, look at which one of those variables that's listed up there, which would be the easiest. To solve for the x with the 2x, you'd have to subtract the y, then divide by the 2. 2 steps. If you solve for the x in the negative 4x, you'd have to subtract 6y and then divide by negative 4, which would be a mess in itself. And so to isolate the y in the first equation, all you had to do is subtract the 2x, and that's what they did. So it's usually the best one to solve for is the variable without any coefficient other than 1. So if you have a coefficient other than 1, so then then that one would be more complicated to solve for. So you got to be careful with that. Now, well, what if they all have coefficients in front of it? Well, to be quite honest with you, if you do it by substitution, you're just got to have to grin and bear it. You're just going to subtract and do that 2-step process. But I'll tell you the truth. If I have a choice, if I have no variable that has isolated with a coefficient of 1, I will use the substitution if that's the case. But if I don't have it, I will use the elimination method. So for example, if that was a 2x plus 5y equals negative 1 instead, and every variable had a number in front of it, then I would not even use substitution. I would have used the elimination method. So that's your first hint, is when you are given a choice, and a lot of times you are given a choice which one you want to use, but if there's numbers in front of every variable, elimination method is the best way to go. The only time I would like to use substitution is when one of the variables has a coefficient of 1. Sometimes there's more than one, and you get to pick which one you want to do. Okay? So you got y equals negative 2x minus 1. So what we're going to do now is we're going to take that negative 2x minus 1, and we're going to substitute that equation into the second equation. So remember, you got negative 4x plus 6y equals 42. That's your other equation. So, but what is y? Well, y is negative 2x minus 1 by the step process above it. So I pop that in there, and you get negative 4x plus 6 times negative 2x minus 1 equals 42. Look what you have now. You have an equation that only has one variable in it. So by chapter 1, section 1, I mean, it was the very first thing we did this semester, chapter 1, section 1, we can solve that equation for x. Okay? So solving that equation for x, we get x equals negative 3. So you distribute the 6, you'll get 6 times negative 2x, which is a negative 12x, and 6 times negative 1 is negative 6. And then you combine some terms. You get negative 4x and negative 12x is negative 16x. Minus 6 equals 42. Okay? And then you add 6 to the other side, and that gives you 48. And then 48 divided by negative 16 is negative 3. That looks familiar, doesn't it? X equals negative 3. So then what you do, since x is negative 3, we're going to go back into one of the equations that you solved for the 2x plus y equals negative 1. You're like, well, why did they choose that one? It doesn't really matter which one they choose to do it. You can put it in any of the two equations that you have. They chose 2x plus y equals negative 1 simply because y has that coefficient of 1. So they put the negative 3 back in for the x and then solve for the y. And you get y equals 5. If you recall, when we were looking at that graph, okay, when we were looking at that graph, this is just a check right here. So we're checking the negative 3 and 5. It works for both of them. So negative 3, 5 is the solution to the system. So it's working for both. Now step 5, I will tell you the truth, I don't really use the check. I don't check it normally unless I have a lot more time at the end of the test. Negative 3, 5 is the solution to both of them. So if you get through a step 4, you found the solution unless you made a calculation error along the way. So step 5 is checking against that, making sure you didn't make any calculation errors. So negative 3, 5 is working for both equations. So that is where they're going to cross. But if you recall, when we did that graph on the previous slides, negative 3, 5 appeared to be where there's two lines actually in a cross. So the red one and the blue one, they crossed that negative 3, 5. I'll show it to you here. Here it is. So we had negative 4x plus 6y equals 42. And then we also had that 2x plus y equals negative 1. And then they appeared to cross, we said, kind of look like it looks like they're negative 3, 5. And that's actually where it is. Okay, so that kind of affirms what I was saying, that the graphs appear to be crossing at -3.5. But you don't want to rely on that graph only to do that, because you can be slightly off on your graph. And again, sometimes these things don't cross right on the integers. You might have a solution of 2.5 comma 5.7, and there is no way your graph is going to give you those points, because you're not going to be able to get it that accurate enough to get those points of intersection. So you can have an intersection there, but the algebra won't lie to you. When you solve that equation for x, and if the x is 2.3, it's going to say 2.3 in that setup. So, but graphs can kind of be deceiving a little bit. So the graphs are nice to kind of tell you what's really going on, but I wouldn't rely on it totally. Alrighty? So, but that's how you do it by the substitution method. So you solve for one of the variables in one of the two equations. It really doesn't matter, but try to pick the one that has the coefficient of 1 in it. Pick that one to solve for. So and then once you do that, substitute that expression into the second equation, your other equation. Now understand, you might be solving for the variable in one of the equations, and then the equation that you solve for is in the second one. Well, in that case, you'd have to put that expression back into the first equation. So it's sometimes for students, it's easy to go from number one, the first equation, to the second equation. But you can solve for the one of the variables in the second equation and sub that back into the first equation. So students usually love this. It's a pretty easy concept if you just kind of pay attention to what's going on. The biggest challenge here is not the technique, it's more of the algebra, making silly mistakes along the way. So you got to make sure you're doing that. So, alrighty. So, but anyway, that concludes the solving the system by substitution. Now, I want you to notice closely though. This system actually did have a solution, -3.5. We are going to come up in a few other objectives that come down the line when they don't actually cross, and we're going to see what happens in that case. Okay, but that concludes this video. If you have any questions on it, if you want to see more examples, you know how to contact me. And as always, you have a good day.